Bismillahirrahmanirrahim. So today is week 14 of the course, and I today plan to talk about regression, completing the deep sequence modeling, and another very important topic, which is transformer. And as I have been dedicating most of the weeks to people, today I want to dedicate this week to these 8 people who are author of this very remarkable paper, which says attention is all you need. So this is a very fundamental a paper that has changed so much, that is used in all large language models, and many generative AI applications. So today we are going to learn about this attention is all you need. So it looks like a very dramatic topic as well, but it's a very highly technical paper. Week 13 was I requested Dr. Amjad to conduct a workshop on fine-tuning LLM, and I hope that you have learned, and this is a skill which is, I think, very valuable. And I have seen some of the people have proposed their term project also in this area, which is fine-tuning. So I today intend to cover regression, because most of the time we have focus on classification, but because you use almost the same algorithms, so learning regression is very simple. So we can just easily learn regression. And then there are 2 things which we briefly touch SVM, but today we'll spend a little more time learning about random forest, SVM. And then we'll switch to sequential deep learning. And we briefly discuss RNN. Today we'll cover RNN, LSTM, and transformers, and then large language models. And so this is kind of what we have covered so far. Is first we focused on, let me see if I can erase. So no issues. So first we focus on unsupervised learning. We learn about KNN, DBSCAN, hierarchical clustering, Gaussian mixed model. And then supervised learning, we learn about the CN trees, naive-Bayes, KNN, neural networks. And then we started focusing on deep learning. So we learn about deep neural networks, then CNN, then few famous CNN, and today we'll cover a few more. And then we also learned about generative AI, GAN especially. GMM is also used, then GAN, and fine-tuning LLM is also like part of generative AI. And then from the policies perspective, we learned about the UAE AI policy, Japan AI policy. In the next class, last class, I intend to just cover the Indian and the Pakistani, what I worked and proposed to the government. And then we discussed several applications. And interesting are the projects, term projects. Everybody is just focusing on an application. So we see a spectrum of applications, and that is also going to make us learn a lot. So that's then is today where we are going to learn regression. So simple linear regression, usually once you see data, okay. So here is an example of data, which is average growing seasonal temperature and the rent of summer resorts. As temperature increases, there is a trend that the rents are also increasing. So sometimes you want to just estimate, like there are some sample resorts where the data is available, but assuming that there may be a location where you don't really know that at this temperature, and you still want to find out that what type of rent should I be expecting to pay. There you need to just look at the trend. If it's a linear trend, so you can just put a linear line. So this is called regression, and regression is different from classification, because in classification, every data point you make it part of a class, whereas regression, there is an exact value on a real axis that you have to predict. That if given one variable, temperature, you got to predict the rent. So it's not a class, you have to predict a number, and which is a real number. So in linear regression is where you have this data and you can see a trend, and you try to fit in a line, and you fit in a line so that these, usually we call this mean square error, is minimized. So a line which basically, all these lines are the error, which are actual data points, and if they all are on the line, then it means that the data basically is of a line, but usually it is not like that. It's just a trend, and you try to fit in a line which minimizes the error. So this is usually, we know the equation of a line, which is y is equal to mx plus c. So you know this is equation of a line. This is c is called the y-intercept, and m is the slope. Okay, so we know that m is the slope. So this is the slope of the line. So there are two variables, two constants that you got to figure out. From machine learning perspective, we call the this y-intercept as b naught and slope as b1. So these are the two parameters that you need to kind of estimate, and given are the points xi, yi. So but usually once you are given this point is not on the line. So there is something which is epsilon I. The point is either above or below. So there is going to be an error, and this is something which we try to minimize. So you can put a line here, you can put a line here, you can put a line here. So there are infinite many possibility. How do you know that this is the line which is going to minimize this prediction error? And you can do hit and trial, but interestingly, from linear algebra, we know that if we can find a closed form solution, that is the best. Like there is a formula, I put in the values, I get the unknowns. So whenever you can represent something mathematically, and then can basically write all this m and c, or in our case, b naught and b1 as a formula, then it is perfect. We really don't have to spend a lot of time in doing hit and trial. And we just exactly know that this is the line which is going to optimize or minimize this error. So this is the slope of the line, and this is the y-intercept, which we need to find out. The formula is the model, yes. So the line, the equation of the line is the model, yes, precisely. So we need to find out b naught and b1, and x and y are the variables. So for these are the estimator. Like if you put a new x, it will give you a new y, which is the estimate. Okay. So what we are trying to do is that, as we have seen, this is the line, and here is the y-intercept, but the points are somewhere here, 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 and here, and these are the error. This is the error, this is the error, this is the error, and this error, let's call this E1. So we need to minimize the mean square error. Sometimes you also divide it by number of points n, but once you take the derivative, it does not really matter. Division will not matter. But the error, we know it is equation of the line, which is this. This is the equation. So it is the actual point, which is, let's say in this case, y1 minus the y1 predicted, which is a point on the line, and you square it. Okay. So y1 is the actual point, which is here, and y hat is the point on the line, and the difference between the two is E1, and you square it, you square it, you square it. Okay, so this is called residual sum of squares, or sum of squares error. And all now you need to do is, once you have a mathematical expression for the error and you want to optimize, so we know you only need to take curly, because there are two variables, beta naught and beta 1. So you take its partial derivative with respect to b naught and the partial derivative with respect to b1, and equate them equal to 0. So that's something we have learned in our linear algebra course, that to find an optimal value of an expression, you take, if there are multiple variables, you take partial derivative. If there's only one variable, you just take the derivative. Okay. So we know that if, let's say, it is x square plus 4x is equation which is kind of a parabola, and you want to find out the minimum point. Okay, so you take dy over dx, which is 2x plus 4, and you equate it equal to 0. So 2x plus 4 is equal to 0, and x is equal to minus 4 divided by 2 is minus 2. So it is basically, it is something like this. So it is 0, minimum is at minus 2. So you can find minimum right away. You don't need to do hit and trial. So that's something very amazing, that there is a closed form.
Is this, excuse me, sir, I have a question
Gigi,
here.
please.
So is this just related to linear regression? Like whenever we are dealing with linear regression, we can use such a strategy to minimize the error to find the mean?
Yes, yes.
Or it is generic and application?
This is generic. As remember, all the back propagation neural network, we were doing almost the same thing, but there the error surface was very complex. Though we were just taking partial derivative, putting them equal to 0. So this is generic, that whenever you have an expression, if expression is like totally convex or concave, then you are guaranteed that this is the optimal. But if something like this, then you don't know, because now there are many local minimum, and you may get trapped in a local minimum. Okay. But as we know that this expression is the sum of the squares is an expression which basically is concave. So it is guaranteed that your error surface will give you the optimal point. So this is a generic technique whenever you want to optimize something and there are number of variables. You always take partial derivative of the expression with respect to one variable, then with respect to the other, and then you make them equal to 0. And once you make them equal to 0, then you can just find a simple formula. So this becomes so simple that here is all the points you are given for the training. This is the average of x, average of y, and all the points that you are given, and you find out b1, and similarly you find out b0, which is all the average of all the y's and average of all the x will give you, and the b1 that you have calculated, you put it here. So very, very nice closed form expression for linear regression. Right? So we are very happy that and it is guaranteeing that this is the best line. Okay, this is the best line because it's not through iterations that you have come to this line, it is through a closed form expression. So we love to have a closed form expression that can guarantee us that this is the best, this is the optimal, this is the best. Okay, so I'll just fit in a line. So whenever we have a lot of data and you see a trend and you want to fit in a line so that given one variable, I'll give you many examples, you can find out the other. A linear regression is the best way. For example, here you are putting, some company is putting ads on TV and they're spending a lot of money for that, maybe Lipton tea or anybody else. So whenever they spend more and more on the advertisement, they check their sales. And why they spend? Because they know that by putting advertisement, they are going to see an increase in scale. And that's how they justify their investment in advertising that on TV or on other media. So this is kind of real data which shows that by spending more on ad, they make more money. The sale increases. So you can just see the trends, and now you are just. And similarly, here is another example where it's very interesting data. So again, real data where sleep and grumpiness, that you are sad, you are not happy, and you will have like few hours of sleep, but you are really very happy. So grumpiness is the feeling of being slightly annoyed. So that affects your sleep. Okay, that's why I say the peace of mind is very important. So once you have a peace of mind, and so you sleep more. So this shows the real data where they have put in a line, And usually all these medical professionals and psychologists, and they are a lot into these regressions and statistical analysis of the data. And usually this is where they just try to. There's also very interesting real data again. The teen birth rate and poverty level in America, like girls of age 15, 16, 17 having a child relates to the poverty level in America, like where they actually live and how much money they make. So, so people who are busy in doing other things, you don't find them having like the high birth rate in those areas. Similarly, another interesting application, which is a beer. This is beer length. So length is the whole length of the beer, and is girth. Girth is this D, which is right after his head, the area. So it is also like kind of related that more the length, more the girth. So there is a relationship, though they can figure this out by themselves. So this is the total bill and the tip amount. So if you have big bill, you tend to pay a little more to the waiters. And this is again the same thing, advertisement on TV, on radio, on newspaper, and then you can see that which gives you more in terms of sales. So whenever you have this type of a data, you can just throw it and do the scatter plot, and that will tell you that there's a trend. It seems like a linear trend, so you just put in a regression line. Then is the case of multiple linear regression. What if you have multiple variables? Okay, so the expression becomes a bit complex because now there is not a line. If there are like two variables, this is equation of a plane. Okay, so once you have three, then you have a solid, and as you having more and more points, it becomes a hyperplane. Hyperplane is something which is you cannot visualize after like 3 dimension. Okay, so the expression becomes kind of complex. And also you need to worry about that if one variable depends upon the other. If it does not, then there is a linear relationship. But if one variable depends upon the other as well, if it affects the other, then obviously it is not a linear relationship. So if it is a linear relationship, still you have the same. For example, if your sales kind of is, if your sales this is the y-intercept, the TV, the money you are spending on TV ad, the money you are spending on radio ad, the money you are spending on newspaper ad, as if one is not affecting the other. Like it's not that if you are already putting money on TV, then nobody is actually watching or listening on the radio, or it's not helping you to increase the sale. But if they are independent, keeping two constant, and if you increase, like you add in the newspaper, you see increase in your sale, or keeping radio and newspaper constant, you put more money on the TV and you see an increase in the sale. So that is where they are linearly independent, and this is how you can just fit in. So usually here, if there are two variables, let's say an ad on TV and an ad on newspaper, or let's say radio. So there are two variables. So you can visualize it. You can visualize that there is going to be a plane that if you increasing the money on the ad on TV and the ad on radio, you have increase in sale. Okay, so there are points all over the place, and you fit in a line, a plane. So equation of a plane which will depend upon x1 and x2. So y, the sale will depend upon, it's an intercept b0 plus b1 x1 plus b2 x2. This is the equation of a plane. And because this is the equation of a plane, but points are everywhere, so you do the same. Your error is, for every point, error 1 for the point number 1, let's say this is point number 1, is going to be actual value, which is this y1, and your prediction y1 hat, which you put in this equation of a plane and get a value, which will be this point. Okay, so this is your error number 1. Similarly, you have error 2, error 3, error 4, error 5, error 6, error 7. So there are 7 errors, you express them. So sorry, this is the minus sign, and you square it. So then you have error 1 square plus error 2 square plus error n square. So this is your mean square error if you divide it by n, and then you start taking curly error over curly b naught, then curly error over curly b1, then curly error over curly b2, and put them equal to 0, put them equal to 0. So there are three variables. You will have three equations, three unknowns, so you can just solve them. Right? So this is called the so this is what it shows, that you have expression like this, then you have this residual sum of square errors, and this is the expression. And again, so you minimize the this by taking partial derivatives and putting them equal to 0, formulating equation, finding out the unknowns, and put a plane. And once you have a plane, then you know that this is how much you are going to spend, this is how much you are going to see the increase in the sale, and then you can budget it accordingly, that how much sale you are targeting, and you have to invest actually in the advertisement, that how much you are spending on the radio, how much you are spending on this, and this is your target sale. So if you give a target, the marketing team will come back to you and they say, give us money for putting an ad here, give us money to put an ad here. Okay. Now there is also a machine learning perspective to linear regression, because we are interested in machine learning where we have features. For example, we discuss about the housing prices or the movie recommending system. So there we have many features, like it's in which area it has, it's a kind of an area, number of bedrooms, and this and that, and so there are many features. Okay, and once we plot them, we see there is a trend, though we cannot plot many features, but let's say there is a trend that if area is increasing, number of bedrooms are increasing, for example, then the price of your housing unit is also increasing, and you want to just predict. And this is something very real problem, where knowing this data, you want to predict that how much should housing unit cost you. So in machine learning, we have seen a classification where this is, remember we said you put a jacket if the temperature is negative, it's cold, and you don't put a jacket if it is hot. But in this case, regression is a line where you have this feature, and then you got to decide about a value on a real axis. So this is regression. There is a value and almost the same thing. And you may want to put a sigmoidal, and as we put sigmoidal, and sigmoidal in regression is going to minimize the error. So always it is going to minimize the error. So this is a classification problem where you have to classify between one class and the other, and you put a separator. And this is where you got to estimate. So all these points, you want them to be closer a plane, which basically minimizes the error. Okay, so this is the classification where one side of the plane has one class, the other side of the plane has the other class. Okay, so if from the machine learning perspective, usually we say these are the weights, theta and theta naught. So we write our expression as theta naught. This is usually the bias, which is not multiplying with any feature. So there is a bias that sometimes you need to have it in your model. And then this is feature number 1 and its weight, feature number 2 and its weight, and similarly feature number n, and so these are the features, x's are the features, and these are the weights. So if this is the problem, in which you can, in the vector form, you can write a theta transpose, which is a vector theta 1, theta 2 up to theta n. So this is a vector. Okay, and x is also a vector, which is your feature 1, feature 2, and feature n. So this is the vector form of the equation. So this is the vector, and once you multiply this vector with this and with theta naught, it gives you a value y, which is your equation of a plane, kind of hyperplane. So again the same, there is a loss function. From whatever we have learned is that you make a loss function. This is what you try to optimize. So you minimize the loss. The loss is same, that this is your equation of the plane and this is your actual value. For every data point you have an actual value. So you have the summation for every value you are in the hyperplane and you have the actual value, the difference, and the square. And then you're dividing it by n. So this is the loss function. And once you have this, you can write it in vector form like this. So this is the vector form of the loss function. And then, so this is a matrix where you have first sample, it's D features. Second sample, D features. Nth sample, D features. Okay? And these are for every sample, you have a value of the house, value of the house, value of the house. That is the training data you have. So you take the training data and you come up with the weights so that if you add a new sample, you can predict its price or value. Okay? So if you, and it's again same that you have to minimize. And how you do this? Curly j over curly theta 1, then curly j over curly theta 2, and curly j over curly theta naught, and you put them equal to 0, equal to 0, equal to 0. So if you do that, interestingly, you get an error. Here is a hyperplane, here is a problem. That you may be, this is ideal, that you know that this is going to be a minimum. So you have a surface like this and there is a minimum. So it guarantees you that you will hit a minimum. But if it is like this, okay, there is no minimum. No matter, you can go down, 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 and you always find a minimum, always find a minimum. And here is like there are many, many minimums. So it is a curve like this. So there are many minimums. So these are all the possibilities. So though you have this, but if it curves up, okay, it curves up like this, then this is the best for you, because now you are guaranteed that you can find a closed form solution. And how do you find a closed form solution? By taking its derivative, or we call the gradient, okay, of this with respect to every theta, and which is this, and you put it equal to 0. And once you put it equal to 0, so this is the gradient, and you put it equal to 0, and once you put it equal to 0, so this is the closed form expression. Wow. So these are your features. Remember, x are your feature vector. So this feature vector multiplied by its transpose will give you a matrix. You take the inverse of the matrix. So this is again a feature vector, and this is your actual value vector. So that will give you all the thetas in a go. So it just like this. So you have all these matrices, take the inverse, multiply it with this vector, multiply it with another vector, and you are done. You get all the features by just solving this equation. So you love to have a closed form expression, and which is, it curves up is important. So it curves up, okay? So if it curves up, you are guaranteed that you are going to have. But now there are use cases, because a hyperplane, there are so many features, you are not really sure that how they are behaving because you cannot plot them. But let's say if you can plot them, and you have wrongly have two features which are highly correlated, like this is a temperature in degree centigrade and this is a temperature in degree Fahrenheit. And you know both are going to have a relationship, because a relationship is basically a formula. So though it is in 3 dimension, but you have a line. And in this line you can fit as many planes as you want, because a line, you can have a plane like this, you can have a plane like this, you can have, you can have different planes, because it's just a line. A line can pass infinite many planes. So you are stuck. It is same as if you are trying to fit in a line into just one point. So all your samples are falling on the same point. So you can have infinite many lines passing through a point, because you don't know that which is actually the line. So you have all these lines. So these kind of use cases would require people, and also there's a problem of sometimes overfitting, that you are trying and then there's a problem of overfitting. So that requires people to learn about we call regularization. So you have another factor that you put into the function, which is we call this linear regression with square penalty, and this is called the ridge regression. So whenever you are using linear regression, you can actually try out a lambda, which will help you to basically regularize. and have your data less dependent upon the training. Otherwise, what happens is that you have a data set, you divide it into training. This is the second problem. You have training, and then you have here testing. Okay, you keep 30% for testing, for example, 70% for training. So you fit in a line or a plane based on the training data. And once you try it on the testing data, you find out that your error is too much, okay? Because it may overfit, it's just focusing on this data. So then for these type of scenarios, people would like to regularize. They add a penalty, and where they are forcing these weights to tend to 0. If for lambda, for example, depending upon, because it's a minimization problem, if it's a minimization problem, if you have high value of lambda, okay, lambda goes to infinity, then theta tends to infinity, theta will tend to 0 because you are trying to minimize. So lambda would control the value of thetas, as you can see here, that these are once lambda is equal to 0, so it is just normal regression. As you start increasing lambda, because now there is a penalty, you want thetas to be smaller and smaller, as much smaller as possible. So they tend to be smaller, 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 or they'll go to 0 if all the weights will go to 0, okay? And obviously you are going to have a lot of error. So regularization is where you have this lambda, and with this lambda you basically vary this lambda from 0 to infinity to make your model a generic model, not exactly specific to the training data. So you leave a little leverage, and then once you are basically putting training data, then you can see what is the optimal value of lambda that you should use to get the best result, okay? So this is the lambdas, and this lambda would also ensure that it is always curved up. So it will make the expression guaranteed that the closed form solution that you are getting is always going to have a minimum, okay? Though it depends upon your selection of lambda. It means you got to be now make sure that you are selecting that lambda. For every value of lambda, there is going to be a curve, okay, which gives you the minimum. So which lambda should you select? So obviously then you have to try different values of lambda. But here is a closed form solution. Now you see it looks very similar to the one which we saw earlier, that there is a transpose and x. But if lambda is 0, then you need to take inverse. It is exactly matches with the previous closed form solution. But if you have here the lambda, then you are adding something more into the matrix, and then you are taking the inverse, and the dimensions is such that they matches with the one which we saw earlier. So this is called regularizing, okay? So regularization is common in almost every machine learning algorithm, that you can regularize and ensure that you always have this by just having this lambda thing in the expression. And so this is called ridge regression, where by increasing value of lambda, this is log of lambda. So 8 is like 8,000 something, okay? So this is the log, and as you keep increasing lambda, your betas, okay? Sometimes you use thetas in the machine learning, and statistics you use betas, b0 plus b1 x1 plus b2 x2, you know? So they are. So this is the value that how if you see the lambda changing. Negative values of the log means it is less than 1. Still greater than 0, but less than 1. For example, if it is 0.1, so it is minus 2 something. Okay? So it is 0.01, so it is minus 6 something. Okay? So it is still positive. Lambda is always positive, but if it is a fractional value, so you will, this natural log is negative. Okay. So you see that once you are increasing, it will increase the error once you are increasing, because now you are just forcing the weights to go to 0. And once they are 0 means they are not really helping you at all. So And this is the second normalization, regularization, which is called lasso. Lasso is where you take the absolute value. The difference between ridge and lasso is that in lasso it will make sum of the coefficients equal to 0. So for example, if you have 10 features, B0, B1, x1 plus B2, x2 plus B9 or B10, x10. It means there are 10 features. Ridge will never make any beta equal to 0. Okay, ridge will ensure that they all are non-zero. So they are always in the model. But lasso, if there is a feature which is not really helping you out, it will just make it equal to 0, the beta equal to 0. The beta equal to 0, so these are different betas. A beta equal to 0, let's say beta 1 is 0. So it means x1 is not really contributing anything into the regression. I'll just remove it. So you can also do a feature reduction by having this normalization, the regularization. The lasso regularization will help you to reduce. So it also does features. So here are the number of features. As you can see in this example, it's a real data. I've taken this example from real data. Features are always 299, 299, 299, 299, though you have very high value of lambda. Okay, this is log of lambda, remember, it's in 1000. So though error is a lot, but it is not dropping any feature. But here, if you look at this, you are dropping features. So here also you started with 15 features, and here you have only 3 features. Here you have 6 features. Here you have left with 12 features. Similarly, here you started with 291 features, but here you have only 51 features and 5 features. So you also can do feature selection by using this particular regularization, which is really help. So here is the so you are minimizing the mean square error, but at the same time reducing the number of features. And this is how it shows that how the value of lambda is basically helping you to find out minimum features and the minimum error. Okay, so I asked ChatGPT, can we use linear regression function with regularization? Okay, and this is what it returned. Absolutely regularized linear regression such as ridge, which is L2 means square regularization, or L1 mean absolute lasso, helps prevent overfitting and improves model generalization by adding regularization term to the cost function. Here is an example using the ridge regression. So he said, yes, I can use it, and here I'm using the ridge. So here you can see the ridge, and here you can just go and change the value of alpha. Okay, alpha, you can just go change the value of alpha here, and here is the Boston data. It is the housing data, and you split it into the test size is 0.2. So you have 80% for the training, 20% for the testing, and you just fit in here, and you say I'm going to use a regularization term, and then you have this model, and you find out the precision, the mean square error. Okay, then I ask it, can we use cross-validation to select best value of lambda? So whenever you have regularization, you got to use cross-validation. Let's say 10-fold cross-validation, where it will split into 10 pieces, and then it'll use 1, 1, 1, 1, 1, and then it'll show you that how you are improving. So it says yes. So this is the code the ChatGPT has generated, where now it is basically using the cross-validation, and I ask it to give me the best value of lambda. So it says best value of lambda is this 2.47707. So now one is just linear regression, that you just use linear regression. The other one is you use linear regression with regularization, and with the regularization then you need to find out the best value. First you need to find out which regularization that you are going to use, because there is lasso or ridge, and then you say, okay, I use this, and then you can find out that how good it is performing, as you can always plot the mean square error, and you say this is performing better than this, so let me use this. So you got to do hit and trials to get. And there is yet another method, which is the gradient descent for linear regression, and we know the gradient descent is iterative method, that you have an initial set of weights, and then you have this update equation, and lambda is also here, and then they just keep repeating this. So keep updating weights. This is the theta 0, which is the bias, and this is rest of the weights. And so you just keep iterating. And we have seen that this is always in this form, that you have the teeth theta, and there is the previous value, and there is this step, learning step, that how fast you want it to adapt, and then you have an expression here, which is the expression of the error. So this is the error. If you look at this, this is the error. So expression of the error, and then it is multiplied by some other thing. So always it is going to be like this. So this is the error. So here is the error. Okay, the mean square error.
This is the feature reduction also doing in principal component analysis.
Principal component analysis is different. Principal component analysis is primarily perform a linear combination of features. So it is feature transformation as well. Okay? And here you are just exactly removing a feature. You're saying this feature goes out, this feature goes, this feature goes. In PCA, you don't know, because in PCA, you basically, there are different eigenvalues, remember? And then you are multiplying it with the that particular smaller eigenvalues are just making the effect of a feature in the principal component smaller. So it just gives a weightage or a value to every feature, that how much valuable a feature is. If a feature is more valuable, its eigenvalue will be greater, and then it'll have more impact. So that is also used for feature reduction, and this is yet another technique. Okay, and what if the data is polynomial? So sometimes you know that you cannot fit in a line. Okay, so you know that the data is, for some reason, it is like this. So you say, if you're fitting a linear regression, so you know that the error will be a lot more, because you say that, oh, there is a lot of error, so it's not really. So it means you have to fit in a polynomial. Okay? And now I start making things complex, because a polynomial, and once it is polynomial, you take derivatives, so you get a set of nonlinear equations. Then you have to solve the nonlinear equations, and so the problem becomes a little complex. And if it is higher degree of polynomial, like say 20, the same data, this is overfitting, that you are putting a 25th degree polynomial, it's trying to go through most of the points. Okay, so you make the problem very, very complex. Okay, because it is a 25th degree polynomial that you are trying to fit into the data. For example, here is the data. You fit in a line definitely you check the error. You fit in a second degree polynomial, you fit in a third degree polynomial, and then you can see that what type of error you are getting. And then you fit in a 20th degree polynomial. So maybe error, you may make the error equal to 0, because now there are 24 points or 21 points, and if 21 points, you can have a 20th degree polynomial to go through every point. And you say, wow, I have reduced the error equal to 0. But as soon as you are going to see some training data, testing data, you will find out the error will be too much because of the overfitting. So overfitting would always that you reduce the training to 0, but once you test it, you have the error, and you have a lot more error than what you were expecting, and that tells you that you have overfit a model. Okay, so you made it very, very complex. So it is underfitting, it is perfect fitting, it is overfitting. So usually you have three cases. Either it is underfit, so the data has some nonlinearity in it, but you are just trying to fit in a linear line. So it's better that you find out that what degree of polynomial you should fit in. So it is always a trade-off between a bias and a variance. Bias is fitting in the simplest model. And if the model requires a bit complexity and you are trying to fit in a simple model, so there will be a lot of error. Okay? And you are trying to make a very complex model, so the error will be this. So this is like variance is the complexity of the error. So you are making the model more and more complex. Is overfitting, and again you have a lot of error. Okay, so you got to find out a sweet spot where you have the complexity which really deserves that type of error. Okay, and sometimes you can have your features, and you can do the feature mapping and convert them into linear features. Okay, maybe you use polar, you convert them into polar coordinates, and you find out now you can fit in a line or a curve. So you can also do this. For example, here it seems like that if you have polar coordinates, or if you take this transformation of a feature and you square them, or even if x1 square plus x2 square, so, and you have kind of center here. So all these negative points will have smaller radius, and all the positive point will have greater radius, and you just plot them r and theta, and you will find out that you can easily fit in a line. So sometimes you can do this, the linear classification with polynomial features. The second regression is the regression trees, and we know, we have learned about decision tree. Remember that you have given a data, I've given you a question in the exam as well on the decision tree, that you split the decision tree. So you have these, all these are the variables: x1 date on which you go to see a doctor, your age, your height, your weight, your sinus tachycardia. If you have sinus tachycardia, minimum systolic blood pressure, and your latest diastolic blood pressure minimum, and this, all these features. And then you find out that you have high risk of heart attack if you have minimum systolic blood pressure of this, and if you age greater than 60, still you have sorry, high risk, yes, low risk, but if this, then you have high risk and low risk. So the leaf nodes are where you put them in a class. So the decision trees are where you have these all these features, x0, x6, x2, x5, and you put them, and then you can give a class label as well, like high risk is 1 and low risk is -1. So it becomes a decision tree. Now you get a new data point, and you can run it through this. So the date has no value, but you have x1, x2, x3, x4, x5, x6. Okay, so x6 is important. So you take this value and pass it through the tree, and the tree would tell you whether you are at high risk or low risk. Okay, because of the decision tree. So this is also can be used for regression. So almost every machine learning algorithm can be used for regression and as well as for classification, and depends upon the data, because now here the data is, if temperature is this much, precipitation is this much, you run these many kilometers. So if x2 is precipitation is greater than 0 to 3, you run 3 kilometer. Otherwise you check temperature, you run 2 kilometer. Otherwise you check this, you run these many kilometers. So you make a decision tree, but now the output is not a class, it is the number of miles you run. So your decision space is something like this, where every node is making a partitioning into your decision space, and here is a value, a real value, which is a real value. So we call this as a regression tree, okay? A real value. Another thing which you can use is neural networks, okay, for the regression again. So now, because we know the neural networks, that there are the bias and the weights and the node and the nonlinearity. Okay, this is the nonlinearity, okay, sigmoidal nonlinearity, and it'll just give you a value. So if linear regression means that you have just up to here, okay, it's just you are multiplying, this is the equation of a line actually, b plus w1 feature 1 plus w2 feature 2 is a equation of a plane. So it's a linear regression, right? So as you put this nonlinearity, which is, it becomes a logistic regression, like it is curved like this, okay? So it becomes a logistic regression. And if you add more layers, it becomes a really shallow neural network. Many layers, it becomes a deep neural network. But end of the day, you have just one node at the output, and which is giving you a real value. Because your backpropagation algorithm, if it is, let's say, value of the house, and you say this is what I have predicted through the network, and this is the actual value, so you take the square and this is the error, and this is the error, you just take it out back, and using the backpropagation algorithm, you tune the weights and keep doing this, so that your neural network is trained. So here is you get a real value. So your output is not giving you a class, it is giving you a real value. And by putting a feature vector here, you can do the prediction using a neural network. Okay. So for example, car price, you have many features and you have a lot of data for the training. And now I'll just give you, based on the model and the year and the engine and the type and this and that, I'll just give you a value. So I asked ChatGPT to train me a neural network to perform regression on benchmark data set. Usually whenever you ask it, it'll take the Boston housing data set. So this is the Massachusetts, the Boston, a city in Massachusetts, and there are all these other features which they have gotten from Bureau of Statistics, which is per capita crime rate and portion of residential. So there's many features which are there, and this is data, something like these are some of the samples of the data. There are, I think, 9 or 10 features, and I ask it to, so you can see that values are really varying a lot in Boston city depending upon where your property is. So the value are varying a lot. So I've lived in Boston for 1 year actually, interestingly. So values just vary a lot. Okay. So I asked ChatGPT to train a neural network. So this is interesting that it has actually trained a neural network where it says 64, it's the layers 64, 64. So it has like inputs, and then there are 64 of these, then there is 64 of these. And I think this is 16 features. So 16 into 64, first number of weights, and then 64 into 64, second layer of weights, and then is the value. So this is 64 into 1. Okay. So as you can see here, it says sequentially putting in layers, add layer, and making it dense, and then it just compile, it just try to fit in from the training data, 100 epoch, and batch size 32, it just do the training, and here is very interesting, very good model. So always the training will do better, and this is the testing. So a pretty good neural network it has trained, and it has just shown. And then I asked ChatGPT to actually show me the network. So this is where the 13 nodes, so 1 to 13 features going to 1 to 64 nodes, and then hidden layer 1 to 64 nodes, and then this one. So you can see 64, 64, 64, 1, 13, 64. So this is the neural network it has trained, and I said show me the weights. So these are the weights. First layer weights 64. These are 64 into 13. So 64 into 13 weights are shown, which after the training, this is what it has gotten. So you can ask it show the next layer weight and the next layer weight. So there are 3 layers. So these are the weights here, which is 64 by 13. Right? This is 64 by 64, and this is 64 by 1. Right? So these are the weights, and so this is how you primarily can train a neural network. There's another thing which I want you to just know is called the transfer learning. You can find a pre-trained model. So the model, people usually they train a model and put the data set on which it's trained and how good it is performing. And now you have a similar application, and what you can do is you can only have some of the layers which you just retrain or fine tune. Okay. So this is called the transfer learning, where you have the pre-trained layer, so you log them, you log these weights, you're not going to change these weights. In the backpropagation neural network, you only backpropagate and train these weights. Okay. For here is an example where something is trained on this ImageNet data set. So you have all the convolutional layers, and then you flatten, and then you have this fully connected layer, and these are, let's say, 10,000 or 1,000 of classes. And now you basically, there is another data set. You say I have another data set, and I freeze all these things because all these are just extracting features, and then you only do these layers, the dense layers. So you just backpropagation neural algorithm network. You say only train these layers for my specific application. So for example, here is the VGG16 is used for the ImageNet, and then it is used to do something else for the training data. Okay, so this is for the ImageNet, and this is a fully connected layer, and this is for detecting cancers, the skin cancer. So two very different applications, but you are just using transfer learning, and all you are here predicting is a label, whether it is benign, malignant or not. And everybody is like kind of doing this. So many papers you will find with do the transfer learning, and it is not only the fully connected layer. You can actually train the so the transfer parameters, some of the convolutional layer, and then you just copy. So I was just working with a student at Georgia Tech, Pakistani student. So he like tried retraining few layers, and he's getting better results. So you can do that. And through backpropagation. So you lock this, you lock this. You're not going to change these bits, and these are unlocked. So through the backpropagation, once you run it, you stop here. Okay, so you're just minimizing the error, minimizing the error, minimizing the error, and whatever you intend to read. Or sometimes once you have features, you can use any classifier, a random forest, you can use SVM and through softmax. So it's not even necessary that you still use neural networks. So once you have features, you can try other. So this is, I think it's an Indian, some Dr. Amit Ray, and this is from his lab. He has all these models, pre-trained models, okay? And he's saying he has 21 key CNN architecture. His students are using these for transfer learning. So it's interesting, he said. So, as we have seen, that once you have set of features, so even in the neural network where you flatten your convolution